Hello everyone, welcoming you to Shourabh's classes. And today we are looking at General Economics Paper 1 of IES 2022 and question number 12 over here and part A of the problem at first. So the question is, what is the Leontief inverse matrix and what are the mathematical properties of it? Okay, so basically now we need to go for the input output analysis. All right. So what basically happens is that, without going into much of the details of anything, let us suppose that x is the vector of output produced by different sectors or industries, whichever one you want to take. Produced by, let's say, different industries. Vector y is basically it's a vector of final demand for the output of these industries. Vector of final demand for the output of different industries. Okay, and let us denote A as the factor coefficient matrix. Okay, like for example, like if many of you are not familiar with this term, let's say we have two sectors, sector 1 and sector 2. Okay, sector 1 produces the output level x1, sector 2 produces an output level x2. Okay, that means your capital X, which is a vector of output, will be x1, x2, and capital Y, which is a vector of final demand, will be y1, y2. Okay, and your factor coefficient matrix will be denoted as A11, A12, A21, A22. Okay, now let us see what do I mean. Now let's, for example, I interpret this term A12. What does it mean? It basically means the number of units of sector 1's output required to produce 1 unit of sector 2's output. That means how much of output of sector 1 needs to be pushed into sector 2 to produce 1 unit of sector 2's output. Units of x1 required to produce 1 unit of x2. This is what it means. That means we will define it in this term. It is basically x12 by x2, where what will be x12? It is units of x1 going into production of x2. Okay, this is what the factor coefficient matrix means. That means similarly you can define all the others. And note one thing which is very important over here. All of them are greater than equals to 0, right, for all ij. Either you don't require a particular sector's input as an intermediate input in the other, or you require something. So it has to be greater than equals to 0. And AII is less than 1. What does AII mean? For all I. Sector I's output going back into the production of the next unit of sector I. So obviously the entire output that you have produced, you are not going to push it back into the production of the next unit. It will always be a part of the output. So AII is less than 1 for all I. So this is the definition. and I'm not going into the computation. What you get is that the final production is basically I minus A whole inverse times Y, where this is known as the Leontief's inverse. Okay, let me just write down once more, is the Leontief inverse. So basically what we are told is, so that is where denoted as L often. So we need to basically find out, like we need to basically mention some of the interesting mathematical properties of this thing. Okay. Now, before going into this, there are a few things that I want to mention about this A matrix, the factor coefficient matrix. Aij is greater equals to 0 for all ij, right? This is often written as the matrix A is greater equals to 0. Okay, alright. And by definition, how can you write xij? Sorry, aij. It is units of sector i's input going into sector j, right? So that will be capital X of ij divided by xj. Okay, fine. That means if you fix a particular j, and if you take if you sum it over all the i's, you get something like this, right? Summation I running from 1 to n aij is equals to summation xij by xj, summation I running from 1 to n. So 1 by xj will be out because uh, sum is over I xij, isn't it? Perfect. Now note one thing. What is summation x, summation I running from 1 to n xij? So it's basically x1j plus x 2j plus so on till x nj. How do you interpret this? For example, x1j, units of industry 1's output, industry 1's output going into production of industry j's output, right? Now naturally, if you collect if some portion, if some amounts from all the n industries are going into sector j, it will not add up to the total amount of production of sector j, which is xj, right? Because in order to produce xj, he required some labor, capital, and things like that as well, right? So this will be lesser than xj. Okay, because factors of production, because factors of production are also needed. I hope this makes sense to you. That means if you just go back, therefore, summation I running from 1 to n aij was basically obtained to be 1 by xj summation I running from 1 to n xij, which is less than xj by xj, which is equals to 1. That is, summation I running from 1 to n aij is less than 1 for all j. So there are two important features. One is your A greater than equals to 0, the A matrix, and this thing. Summation I running from 1 to n aij is less than 1 for all I, for all j, sorry. So with this idea, what we want to see is some interesting properties of this Leontief matrix. So let me just write it down. The Leontief inverse is defined as L, which is equals to I minus A whole inverse, where your capital A is greater equals to 0 and summation I running from 1 to n aij is less than 1 for all j. Okay. Now understand one thing, this is a very simplified example where we are taking n sectors and all, but in reality there can be hundreds of sectors, right? So the A matrix can be humongous and taking an inverse of that might be a very tedious job. So what we want to do is basically the formulation of this Leontief inverse has some interesting observation which I will call it as the power series approximation of this. That means basically rather than going by the standard classical way of finding the inverse of a matrix, I'm going to use some power series approximation of finding the inverse of this matrix I minus A. So what do I do? Basically, I take this matrix I minus A. My objective is to find the inverse of this, and I pre-multiply it with this sum 1 plus A plus a square plus dot 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 up till a to the power n. Okay, let us see what happens, and then I think you'll be able to understand why I did this or what is the essence of doing this. If you simplify, first I multiply with I, so I times I is a plus a square plus dot a to the power n, right? So this remains the same, minus a minus a square minus dot a to the power n plus 1, right? Can you observe that this a will cancel out with this a square will cancel out with this. So if the last term is a to the power n plus 1, so this a to the power n will also cancel out, and what you get is 1 minus a to the power n plus 1, correct? Now observe one thing, since all the elements of A are positive and summation I running from 1 to n aij is less than 1 for all 0, that is, if for large n, that means a large number, if n tends to infinity, then actually a to the power n plus 1 tends to 0. Then what will happen? Therefore, I minus a times I plus a plus a square plus dot a to the power n is simply I. Now, do you understand that what we are doing? We are multiplying two matrices, one is this and another one is this, and we are getting identity. So this statement, what we have obtained, is simply the definition of inverse. You multiply two matrices and get an identity matrix. So one is the inverse of the other. Therefore, I minus a whole inverse is nothing but this thing, 1 plus a square plus dot. This is the power series approximation that we were talking about. Okay, this is one of the interesting properties of the Leontief inverse matrix that we were required to illustrate. Okay, so now let's move on to the next part of the question, which is part B. State and prove graphically the Hawkins-Siemens condition in case of a 2 cross 2 industries in a static open input-output model. Give an economic interpretation of it. Okay, so coming to part B of the question, where we have 2 cross 2 setup. Correct? So what is the equation that we are looking at? X equals to I minus a whole inverse times y, where in this case your x is will have two components, x1 x2. Your y will have two components, y1 y2, and your A will be a 2 cross 2 matrix, A11, A12, A21, A22, right? Now if you look at the Leontief inverse, it looks something like this, right? I minus a whole inverse. That means I is what? A 2 by 2 identity matrix 1 0 0 1 minus A11, A12, A21, A22, right? That inverse. So that is basically becoming 1 minus A11, A12, A21, 1 minus A22. This whole thing inverse. Correct? Now understand, this is how it is defined. Now what does the Hawkins-Siemens condition basically say? That the necessary and sufficient condition for x vector to be positive should be 1 minus a11 to be positive, 1 minus a22 to be positive, and finally the second one is the determinant of this Leontief matrix 1 minus a11 into 1 minus a22 minus a12 a21 should be positive. Now this ensures, these two conditions will ensure that the final output that you're getting is actually positive. So this is basically the necessary and sufficient condition for capital X to be greater than or equals to 0. Okay, so we want to find capital X. This is the target. The production levels given the final demand for the individual industry's output level. So from this, I can easily write I minus A times X is equals to Y, right? So this will be 1 minus A11, A12, A21, 1 minus A22 times X1, X2 is equals to y1, y2. So this basically means if you just multiply it out, 1 minus a11 times x1 plus a21 times x2 is equals to y1, right? This is equation 1. And a21 times x1 plus 1 minus a22 times x2 is equals to y2. Okay, this is what it means. And now we want to graphically illustrate the Hawkins-Siemens condition. So let us first draw a graph over here. So x1 over here, x2 over here, and 0. Right? Now look at one thing. One important assumption is that aij's are greater equals to 0 for all ij. Okay? And the Hawkins-Siemens first condition was 1 minus A11 positive and 1 minus A22 should be positive. So if you look at equation 1 from here, um, you can write it in intercept form. So it will be x1 divided by y1 by 1 minus a11 plus x2 divided by y1 by a21 is equals to 1. And equation 2 will be likewise written as x1 divided by y2 divided by a21 plus x2 divided by y2 divided by 1 minus a22, that equals to 1. So look over here that a21 is positive and a12 is positive. So these two intercepts are positive. That's for sure. Correct? Now comes this one. Coming to the other intercepts. 1 minus a11 positive means this entire thing is actually positive. So y1 by 1 minus a11 is positive. So the x-intercept is positive and your y-intercept is also positive. Okay, so there has been one small mistake that I would like to rectify before moving forward. So the I minus A matrix will have a minus sign over here. That means these will become minus in front, and this will be minus. Um, there will be a minus in front, and here also there will be a minus. And this is A1. Right, kindly rectify the mistake, then we can move forward. So understand 1 minus a11 positive means the x1 intercept is positive over here for line 1, but the x2 is negative. Okay, it's fine. So this is your positive intercept y1 by 1 minus a11, and your negative intercept is over here, that is minus of y1 by a12. So your how will the line look like in space? Uh, yeah, something like this. This is your equation 1. Okay. And coming to the second one, the x into x1 intercept will be negative, so it will be somewhere over here. So that is minus y2 by a21, and your x2 intercept will be positive because 1 minus a22 is actually positive. So that is y2 divided by 1 minus a22. Okay, so if you just join them, okay, so now look at this thing. As you can see, we want to find a solution in the first quadrant. That means the second line needs to be flatter than the first line in order to guarantee that, right? Because if it's steeper, you can see that they will never intersect in the first quadrant. So the condition that we require to investigate is the second line being flatter than the first line. So I'll just rub this out and place the coordinate ranking over here. This is what it is. This is where you will obtain your equilibrium and your x1 star and x2 star. So understand one thing, the Hawkins-Siemens first condition basically tries to ensure that you have a possibility of equilibrium in the first quadrant, but there has to be another condition to guarantee that you will actually intersect in the first quadrant. So what is the condition? 2 has to be flatter than 1. Right? That is, slope of line 2 has to be lesser than slope of line 1. Correct? So moving on. So what was equation 1? 1 minus a11 times x1 minus a21 times x2 is equals to y1. So 1 minus a11 times dx1 minus a21 times dx2 is equals to 0. So 1 minus a11 times dx1 equals to a21 times dx2. So dx2 by dx1 is equals to 1 minus a11 divided by a21. Correct? And my equation 2 was minus a21 times x1 plus 1 minus a22 times x2 is equals to y2. Minus a21 times dx1 plus 1 minus a22 times dx2 is equals to 0. So 1 minus a22 times dx2 equals to a22 times dx1. So dx2 by dx1 is equals to a21 by 1 minus a22. Right? So this is for line 1, this is for line 2, and this is my condition that slope of line 2 has to be lesser than slope of line 1. That means a21 by 1 minus a22 should be lesser than 1 minus a11 by a21, and that means if you just change sides it will be giving you this, and this basically boils down to writing 1 minus a11 into 1 minus a22 minus a1 a2 a2 a1 is greater than 0, which is the Hawkins-Siemens second condition. So the necessary and sufficient condition to ensure that x is greater than 0 are the Hawkins-Siemens condition. The first condition basically gives you a hint into the possibility of getting the output in the first quadrant, and the second condition basically confirms that you will always get to a unique solution with this idea. Okay. So now coming to the next part of the question, which is part C. Consider the Leontief input coefficient matrix as follows. Test the viability conditions of the system and test the properties of the Leontief inverse. So viability conditions and properties of the Leontief. So there are two things. Viability of the condition means going in for the Hawkins-Siemens conditions, and the properties of the Leontief inverse is basically the power series approximation property. this is basically what they're trying to tell us. So this is the A matrix. So first of all, let us find out the I minus A matrix. So this is basically, I hope you all know, it's 1 0 0 0 1 0 0 0 1 minus our Leontief matrix 0.1 0.2 0.2 0.2 0.4 0.1 0.3 0.1 0.6. So what do we get? Let me write down in the next slide, not hurry now. Is 0.9 minus 0.2 minus 0.2 0.2 minus 0.2 and minus 0.1 minus 0.3 minus 0.1 and 0.4. Okay, so this is what it is. All right, so now we need to confirm the Hawkins-Simmons condition. But for 2 by 2 case, we could geometrically have a view of what the Hawkins-Simmons condition means and all that. So how do we go in for 3 by 3 case? So what basically comes out is that for this is a 3 by 3 case. So what does the Hawkins-Simmons condition state in this case is that all the principal minors of this I minus A matrix should be positive. So let me just write that down. All the principal minors of I minus A should be positive. And that will ensure that the Hawkins-Simmons condition is satisfied. Now, how do you obtain the principal minors? You basically eliminate, for example, you want to find out the second order principal minors. This is the most relevant one. The second order principal minors. So what basically you have to do is that if you eliminate row 1 and column 1, then what is the sub matrix that remains? Take the determinant of that. 0.6 minus 0.1 minus 0.1 0.4 and check if it is positive. Now remove row 2 and column 2 from the setup. Row 2 and column 2 and check for the determinant of the remaining 2 by 2 matrix. Minus 0.9 minus 0.2 minus 0.3 and 0.4. And likewise, if you remove row 3 and column 3, then what are you left? You are left with this matrix: 0.9 minus 0.2 minus 0.2 and 0.6. So you need to check basically whether all these three determinants are positive. Similarly, so second order minors are gone. Now you come to the first order minors. First order principal minors. So what do? You eliminate row 1, row 2 and column 1, column 2. So what do you get? You basically get 0.4, which is positive. Next you eliminate row 1, row 3, row 1, I'm just marking it, row 1, row 3, column 1 and column 3. So you basically get 0.6, which is again positive. And similarly you take row 2 and row 3, 2 and row 3, column 2 and column 3. So that basically gives us 0.9, which is positive. Okay. And finally, you come to the third order principal minor, which is nothing but the entire matrix. So you take the determinant of this and check if it is positive. If all of them are positive, then the Hawkins-Siemens conditions are satisfied. And that is what you are required to check, testing the viability of the system. And finally, after that, you will to check for the properties of that, what they have asked you, that test the properties of the Leontief inverse. So what you can do, since it's a 3 by 3 matrix, you can easily compute the I minus A inverse in the standard way, and then compare it with this I plus 1 plus A square, the odd thing. Basically, what you will find, the more you add the powered matrices, you will see that it is approximating closer and closer to the actual answer. Now, I'm not doing this computation because it's just the algebra that is needed. I hope you have understood the idea and you can work it out yourself. Okay, thank you.